Abby, and in this video I will be deriving the finite differencing equation of a linear bar. We're going to start with what we found when we were getting the heat diffusion equation for Cartesian coordinates. We have some assumptions before we start. We have that heat generation is equal to 0. It was equal to 0 when we were finding this equation as well. We have, this is one-dimensional, so we're only going to be working with heat flow in one dimension, so we're going to pretend that this is only in x direction, that the z and y directions are either very, very small or just non-existent. And you show that by putting the partial derivative with respect to y and z are both equal to 0. And our third assumption is that the heat diffusivity constant is equal to K over specific heat times density, and this is the thermal conductivity constant. We used the inverse of this in the Cartesian equation. Let's label our figure. So this is again a linear bar in one direction. We have length 0 to capital J, and we have the temperature is equal to 350 Kelvin, and the temperature is equal to 400 Kelvin for any time So at any time we want to find the temperature or the change in temperature within the bar. This side is always 350 and this side is always 400, but obviously as the heat diffuses it will change. The initial condition of the bar though is here. So the bar is at 300 Kelvin. 0. So the bar is at 300 Kelvin, and then we're pretty much heating the bar up to 400, but this side will never reach past 350, so there's something either pulling out the heat or it just can't raise to 400. So the purpose of the finite differencing equation is to take segments of a bar. These are all supposed to be equal segments. By the way, these are just arbitrary numbers for the example, but it could be whatever your actual problem is referring to. These are delta x. So again, a position, it's in the x direction, so delta x. We are trying to find what the temperature is at any time in any particular segment. So in order to do that, we kind of have to label our positions. So we're going to label this as T lowercase j and T capital J at the end of the position, or at the end of the bar. Then we will this is at any j, by the way. J, which is position. I realized I forgot that. So now we're going to work with our equation, and it's, as I stated up here, it's the change in temperature over the change in time, which is equal to the change in temperature over the change in position. Ooh, I wrote that wrong. Let's take that. So if we're looking at our change in temperature, T, we're going to have the final minus the initial for delta temperature, and that will be T, Tj at time n, so it would be time n plus 1, because that's the final, so one step or one interval into the future, minus T at the same position, because we want the change in temperature of one particular interval of position or block at time n, so the initial time and the final time, over the change in time, which we'll just use a delta lowercase t. So that's this term. So that will equal to, and then this side of the equation can be kind of simplified into the two partial derivatives. And then this term is just the change in x, so we'll put 1 over delta x. This term will act very similarly to this term, except for we'll be changing the position term, not the time interval. I'll write this out so we don't forget that it's T of j, which is equal to the position to the n, which is equal to the time interval. So let's start writing out this half of the equation. So it's going to be similar. It's going to be T position plus 1, because we want to look at the heat of the blocks on either side. So say this is T of j, this is T of j minus 1 and T of j plus 1. And we want to look at them all at the same time interval because we only want one variable to change. So we'll use n over delta x, and then it'll be minus T of j n over delta x. So this is one term. So this is the change between these two, and then we have to do the change between the one and the one behind it. So this is like final minus initial, and then we'll do another final minus initial. So minus T of j at the end minus T of j minus 1 is the final. So minus T of j of n all over delta x. And then this other delta x, we'll put this entire term over delta x. Then we can start simplifying this equation, and it will be T of j to the n plus 1 minus T of j to the n over delta time equals T of j plus 1 to the n minus 2 T of j. No, it is the, it's this way. It's this way because we're still moving in this direction, so this is the final minus the initial, because we're seeing the difference in relation to this, so this is the final. Yeah. And then if you put in the minus, 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 plus. So watch the sign. I could write this as delta x squared, but I'm going to leave them separate right now. No, I'll just simplify it further. It'll be less confusing. So we've started simplifying our equation, and I forgot the heat diffusivity constant. That needs to be in here because that's how the heat is diffusing throughout the bar. So let me add that in. And then we can start trying to get the final variable that we want to solve for is what is the temperature at this block one step into the future. So this is a variable we want to solve for, so we want to try to isolate this on the left side of the equation and have every other variable on the right side of the equation. So we can multiply the delta time over and I'll write this out. Delta T. So now we have a further simplified equation, so we need to add over this term. This is also known as the constant r, so since this is pretty much a constant, we can just put in another variable and we'll use r. So that will be simplified as well, and I can go ahead and put the like if you separated this into this term times 1 over delta x squared, that can also be in this term. So that's what will make this r. So I'm doing a couple simplification steps in one, but I think it's not too bad. So again, r is equal to and then we have all of this again. So this is the final equation. This is the finite differencing equation. And next I will show you how to use Google Collaborative's Python to graph to find the answer instead of plugging in multiple numbers. But again, I briefly mentioned that this equation is telling you the temperature of a specific block one time interval into the future by using its initial temperature and then how the heat is diffusing with respect to time and position of the blocks right before and right after it on the linear bar.
So we are going to be coding out our derivation of the finite differencing equation. So we are going to start with some common imports. We're going to import numpy as np. We're going to import plotly as no. We're going to put in our subplots So that's a pretty common one. We're going to start defining our variables. We have an x equal to 100, and I'm going to type out some little comments so we remember. And this is for the divisions in the bar or like the delta x. Then we're going to do nt, which is equal to, I'm going to do 20,000. This is like time intervals or dt. These could be different numbers, but we're just gonna roll with these for right now. We have R is equal to 0.1, and that's the heat diffusivity constant times the time. And it's divided by the like delta x squared. And then T is equal to, we're going to do n dot p full nx 300. The 300 is that initial temperature of the linear bar in Kelvin, and we did it as a float, and then we're going to start defining our sides of the bars. So the left side of the bar is at the left side of the bar is at 350 Kelvin and will not change. And then this is a little confusing, but we're going to use the -1 to indicate the right side of the bar because it's kind of a step into the negative, and then that's the 400 Kelvin, and then I'll put right side of bar. And then x is equal to n dot p arrange at x. Okay, and then that's pretty much defining our variables, and now we're going to work on actually making a graph. This is all pretty standard graphing code for collab. The mode will be lines. We put in it in as a scatter plot, so we will be using this lines to connect them so we can see the trends a little easier, and we'll name it the initial for the initial conditions. So for I in range 1 to nt, it's a for loop. It'll be t from 1 -1 equal to t 1 -1 plus r times t from 2 minus 2 times t 1 to -1 plus t -2. Okay. So this equation is pretty much that equation that we found in the last video, or last portion of the video, and it's like the J
and you know, the initial and then the R times the j plus 1, the j, and the j minus 1. So those are those where those ranges come from. Percent 100 equals 0. We'll do figure, and this just says once we've finished the for loop, it will graph. We'll add it to the scatter plot, and I'm just going to copy and paste this to make sure it's correct, because this is the scatter plot we want to add it to. And then we will show the figure. Oop, put in a plus instead of an equal. Let me retry that. And I forgot same thing in this one. Okay. So I found my error. I had a comma instead of a period. So we'll try it one more time. All right, so we're looking at our trends as we go across, the linear bar with time intervals, and it looks pretty good. We're seeing all the different paths. So let's try to change a couple of our values. So let's change our R value to 0.5. We'll rerun it. See how it looks. This is nice. This is a very linear path, which is what we want to see. Shows a good trend. So let's try 0.55. See how it looks now. Yep, now we have all these oscillations. Our equation is now unstable, and so we can't go above an R value of 1/2 or 0.5 because it causes this instability in our equation due to our assumptions, and we will talk about that more in future videos.